Morning inside the habitat begins with a sound, not a sunrise. The low mechanical exhale of an air handler cycling on, followed by the quieter click of a heater, holding the room at a comfortable 21 degrees against -60 just beyond the wall. A resident reaches for a glass of water that was, 3 days earlier, somebody's breath. Condensed, filtered, and returned. The lights rise on a timer built to imitate a day that Mars itself does not provide in any usable form. Every one of these small actions looks, for a moment, like an ordinary domestic routine. Coffee, water, warmth, light. It is not ordinary. Each one is a machine standing between a human body and a planet that would end that body in under 2 minutes without it. The failure that matters here is never the storm on the horizon. It is the failure nobody notices. In the system nobody was watching, on the day the backup for the backup is also busy. This is not a film about reaching Mars. It is about what living there would actually require, permanently, with none of the help Earth quietly provides for free. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Call it a house. That is the word the architecture drawings use, the word the mission planners use in press briefings, the word a settler would use in a letter home, if letters home took less than 20 minutes each way to arrive. A house on Mars is a pressure vessel with furniture in it. Every wall that looks like drywall is load-bearing against a pressure differential that would otherwise try to rip the room open. Every window is a laminated composite rated to survive micrometeorite impact and thermal cycling that swings by more than 80 degrees between a Martian noon and a Martian midnight. A daily temperature range wider than most of Earth's hottest deserts and coldest winters combined into a single 24-hour cycle. Repeated every single day, indefinitely, on every exterior surface the habitat presents to the sky. Materials expand and contract under that cycling in ways that fatigue seals, stress joints, and, over enough repetitions, find whatever weakness a manufacturing process failed to eliminate. A house on Earth built to this standard would be considered wildly over-engineered for its climate. A house on Mars built to any lesser standard would not survive its first year. None of this is visible to the people living inside it, which is exactly the point. A well-engineered home hides its engineering. The question this film keeps returning to is what happens when the engineering is the only thing standing between comfort and vacuum, and whether hidden is a property a home can afford to have when the stakes are that absolute. Start with the baseline, because nothing else in this film makes sense without it. Mars's atmosphere exerts a mean surface pressure of about 610 pascals. Earth's sea level pressure is a little over 101,000 pascals. Do the division and Mars comes out to roughly 0.6% of what a human body evolved to have pressing on it from the outside. There is a threshold in human physiology called the Armstrong limit, a bit above 6,000 pascals, below which unprotected body fluids begin to boil at normal body temperature. Not because the environment is hot, but because low enough pressure lowers the boiling point of water past 37 degrees Celsius. Mars sits at roughly a tenth of that limit. This is not a planet where a damaged suit gives a person a few minutes to find shelter. It is a planet where the ordinary rules that separate outside from extremely dangerous outside simply do not apply. Because there is no outside gentle enough to run to. Pressure alone would be enough to kill unprotected exposure quickly. But the composition of what little atmosphere exists compounds the problem rather than softening it. The Martian atmosphere is roughly 95 to 96% carbon dioxide, with small fractions of nitrogen and argon rounding out the mix, and an oxygen content sitting at well under 0.2%. That is not no oxygen. It is worth being precise here, because the honest version of this fact is more useful than the dramatic one. But it is an amount so far below what human respiration requires that the distinction is academic. A human standing unprotected on the Martian surface does not suffocate the way a diver runs out of air. The pressure problem arrives first, and the atmospheric composition simply guarantees there is nothing to inhale, even if pressure were not the more immediate concern. Two separate hazards, each individually sufficient, stacked on top of each other. That stacking, more than either fact alone, is the first thing any Martian home has to solve permanently without a single day off. So, a habitat gets built, and it is sealed, and inside that seal the air is manufactured to hold pressure near Earth normal, oxygen content in a breathable range, temperature within a livable band. From inside, on a quiet afternoon, it can look and feel remarkably close to a room on Earth. A resident could sit at a table, read, drink coffee, feel warm. That resemblance is the most seductive and the most misleading thing about a Martian home, because it invites a comparison to an Earth house that the comparison cannot actually support. An Earth house does very little of this work itself. Air is already breathable outside its walls. Water falls from the sky and collects in rivers a plumbing system merely has to reach. Heat loss through a wall is a cost-efficiency question, not a survival one. A poorly insulated house on Earth is expensive to heat, not lethal to occupy. The walls of an Earth home are, in the most literal engineering sense, optional. People sleep outdoors, in tents, under nothing at all, across most of this planet's habitable regions, and simply get cold or wet. They do not, absent extreme conditions, die in the first hour. A third analogue is worth placing alongside the Antarctic station because it isolates the pressure vessel problem more precisely than a polar research base can. A nuclear submarine on an extended deployment seals its crew inside a pressurized hull for months at a time, manufacturing its own breathable air and drinking water exactly the way a Martian habitat would have to, running on internally generated power without surfacing. In that narrow sense, a submarine crew lives closer to the Martian condition than an Antarctic research team does. Sealed atmosphere, manufactured water, no casual door to the outside, but the comparison still breaks at the same seam it always breaks at. A submarine remains, at every moment of its deployment, inside Earth's ocean, itself sitting under Earth's atmosphere, still shielded by Earth's magnetic field, still floating in a body of water that is, however many kilometers away, ultimately continuous with rescue. If a genuine catastrophic failure strikes a submarine and it can surface or be reached, the crew steps back into breathable air the instant a hatch opens. On Mars, opening the equivalent hatch changes nothing about the survival math outside it. The engineering resemblance between a submarine hull and a Martian habitat is real and instructive. The planetary context around each of them is not remotely the same, and that context is precisely what a home has to reckon with. That is the actual distinction this film is built around, and it deserves to be stated plainly before anything else happens. Survivable and livable are not the same claim, and the entire discipline of keeping a body alive on Mars is separate. Conceptually, financially, and morally. From the discipline of making a life there, a short-duration mission only has to solve survivable. A crew flies in, works for weeks or months inside meticulously monitored systems, and flies home before anything has time to wear out, run out, or go wrong in a way nobody anticipated. A home is a different promise entirely. A home is not a system rated to function for a mission's duration. It is a system that has to keep functioning for decades, ideally without the option of simply leaving when it starts to fail. The gap between those two standards, mission-rated and home-rated, is where this film spends nearly all of its attention, because it is the gap almost every optimistic account of Martian settlement quietly steps over. Consider what an Earth home actually receives, at no charge and with no maintenance contract, from the planet surrounding it: breathable air, replenished continuously by a planetary-scale carbon cycle that predates the house by billions of years. A magnetic field, generated by a molten iron core still churning with heat left over from planetary formation, that deflects the bulk of the solar wind and cosmic radiation before it ever reaches the roof. An atmosphere thick enough, roughly 1,000 grams of shielding mass per square centimeter directly overhead, to absorb the radiation the magnetic field does not catch. A water cycle that evaporates, condenses, and returns fresh water without anyone building the machine that performs the phase change. A biosphere, however battered, that has spent hundreds of millions of years tuning itself into rough equilibrium with the atmosphere humans breathe. None of these things appear on a household budget. None of them require a maintenance technician. They are, from the perspective of the house, free. Inherited infrastructure so vast and so old that its presence rarely rises to conscious attention. Mars offers none of it. Not less of it. None. There is no global magnetic field standing between the surface and space. Whatever weak, patchy remnant field exists in isolated crustal regions is roughly 1,000th the strength of Earth's, nowhere near sufficient to matter at a settlement scale. There is no thick atmosphere to make up the difference. What atmosphere exists provides on the order of 1 to 2% of Earth's shielding column, an amount close enough to negligible that the surface receives a steady dose of galactic cosmic radiation with only minor attenuation. There is no water cycle delivering rain. There is no biosphere buffering the atmosphere against the machine that manufactures it. Every single item on that free list has to be replaced by hardware, and every piece of that hardware has to work continuously, indefinitely, without the planet's help and largely without Earth's help either. Once the resupply window closes for the length of a synodic period, this is the frame worth holding through everything that follows. Not Mars is hostile, a word this film will try hard to avoid, because hostile implies intent, and intent is the wrong model for what is actually happening. Absent the magnetic field, absent the atmosphere, absent the water cycle, absent the biosphere, and a home built there has to manufacture, from scratch, every piece of infrastructure that an Earth home was quietly handed at birth. That is not a difficulty in the ordinary sense. It is a different category of undertaking. And the rest of this film exists to trace exactly what that category demands, one dependency at a time, until the meaning of the word home itself has to be reconsidered. There is a closer Earth analogue than most people reach for, and it is worth pausing on, because it exposes exactly where the comparison breaks. Antarctic research stations are often invoked as a preview of Martian life. Isolated, cold, dependent on shipped supplies, staffed by small rotating crews. The comparison holds for exactly as long as it takes to notice what an Antarctic station is still standing on. Its air is Earth's air, breathable the instant a door opens. Its gravity is Earth's gravity. At the strength, every bone and muscle in every resident's body was built to expect. Its magnetic field and atmosphere are still doing their radiation shielding work overhead, unnoticed, uninterrupted. A fire, a structural failure, a medical emergency severe enough to exceed the station's capabilities can, in the worst case, still be answered by an aircraft, weather permitting, sometimes after a dangerous delay, but the physical possibility exists. None of that possibility exists on Mars. The nearest unprotected breathable air is tens of millions of kilometers away on a good day and further on a bad one. A Martian habitat is not an Antarctic station with worse weather. It is something that has no true precedent in human experience, because no human dwelling in history has ever had to manufacture literally everything: pressure, breathable composition, temperature, radiation shielding, and water, simultaneously, with no planetary backstop of any kind underneath it. It is worth asking, briefly, why the word home carries this much weight in the first place, rather than simply accepting it as a synonym for dwelling and moving on. In ordinary usage, Calling a place home is not primarily a claim about its walls or its comfort. It is a claim about a relationship between a person and a place. One built from the expectation of staying, the ability to be sick there without abandoning it, the presence of other people whose lives are similarly tied to it, and, crucially, the reasonable assumption that if something goes wrong, the place itself does not become the thing that kills its occupants. A hotel room can be comfortable without being home. A tent on a weekend trip can be memorable without being home. What separates a house from a home, in the way people actually use the word, has never really been about square footage or decor. It has been about durability of relationship, the sense that the place will still be standing, in a form the resident can still live inside, well after this particular evening ends. That is the definition this film is quietly testing against. Chapter by chapter, and it is a stricter test than, can someone survive here tonight? This is also the moment to be precise about what this film is not arguing. It is not arguing that a sealed habitat on Mars cannot be built, or that human beings cannot survive inside one for extended periods. Engineers have already demonstrated most of the individual technologies involved, and later chapters take those technologies seriously, on their own strongest terms, before testing their limits. The argument is narrower and, in a way, harder to dismiss. That can be kept alive inside and can be called home are different claims, resting on different evidence, and that the distance between them is not a matter of comfort or aesthetics. It is a matter of redundancy that does not run out, of a body that tolerates the environment rather than merely surviving exposure to it, of a life that can recover from failure rather than simply postponing it, and of a place a family could commit to across more than one generation without that commitment functioning as an open-ended experiment on people who never agreed to be its subjects. Each of those four conditions will get tested directly before this film is finished. None of them is guaranteed by the fact that the air handler is working this morning. Hold on to the image from the opening. The water that was breath 3 days ago, the light on its artificial timer, the warmth held against -60 just past the wall, because this film returns to it once, deliberately, after everything else has been established. For now, it is enough to notice what that image actually shows. Not a home, yet a save state, a room where survival has been achieved and is being renewed continuously by machinery nobody in the room is required to think about until the day they are. But sealing people inside a habitat solves only the boundary between air and vacuum. It does not, by itself, solve what happens the day one of the machines behind that boundary stops working. And that is where the real structure of a Martian home begins to reveal itself. How many separate machines have to keep working at this exact moment for the air in that room to stay breathable? The honest answer is uncomfortable, because it is not one machine, or even a short list. It is a chain. A pressure vessel holding structural integrity against the differential. An atmosphere processor scrubbing exhaled carbon dioxide back down to a survivable concentration. An oxygen generation system replacing what respiration consumes. A thermal control loop pumping heat where it is needed and rejecting it where it is not. A power system generating and storing the electricity every other link in the chain depends on. And a water recovery system reclaiming humidity, wastewater, and hygiene water back into something drinkable. 6 systems. From inside the room, they present as 6 separate comforts. Air that smells clean, water from a tap, a bearable temperature, light on a switch. They are one coupled system wearing 6 faces. And the coupling is the part that rarely makes it into the optimistic version of this story. Power deserves particular attention among the 6, because it is the one link every other link depends on completely, and because the 2 realistic options for generating it carry genuinely different trade-offs, rather than one obviously correct answer. Solar power is well proven, relatively simple to deploy, and scales cleanly with the size of the array installed. But Chapter 6 will show exactly how dust accumulation erodes its output over time. And Chapter 6 after that will show what a planet-encircling dust storm can do to it in the worst case. Nuclear power, in the form of a small fission reactor or radioisotope generator, avoids the dust and daylight dependency entirely, running at a steady output regardless of storms or the Martian night, but it arrives with its own costs. Significant mass to transport from Earth, specialized handling and safety infrastructure, and a level of engineering complexity that raises its own maintenance burden. Neither option makes the other unnecessary. Most serious habitat architectures propose using both: solar for routine operation, with a nuclear or battery reserve sized to survive exactly the kind of extended, low-light event a global dust storm produces, which is itself a quiet admission that no single power source has yet been judged reliable enough on its own to keep every other system in this chapter running without interruption. It helps to look at what 2 of those 6 links actually do, mechanically, because the word life support tends to flatten 6 distinct engineering problems into one vague comfort. Carbon dioxide scrubbing works by cycling cabin air through a material, often a regenerable chemical sorbent, that binds CO2 molecules as air passes through, then releases them again when heated or exposed to vacuum. So the same unit can be cycled between capturing and venting, rather than consumed and discarded. It has to keep pace, continuously, with however many people are breathing in the sealed volume, slow it down, and CO2 concentration climbs toward levels that cause headaches, then impaired judgment long before it becomes acutely dangerous, which is its own quiet danger, since the earliest symptom of a scrubbing failure is a diminished ability to notice the scrubbing has failed. Thermal control works by circulating a coolant loop past the electronics and machinery generating waste heat, then rejecting that heat somewhere it can leave the system, typically a radiator panel exposed to the Martian sky, since there is no atmosphere thick enough to carry heat away by simple convection the way an Earth radiator relies on. A third link deserves the same treatment, if only because it is the least glamorous and therefore the most likely to be forgotten in an optimistic account. Waste management. Every gram of solid and liquid waste a body produces has to go somewhere, and on Mars, somewhere cannot simply mean a municipal sewage system connected to a treatment plant built decades before anyone currently living used it. A settlement either has to process waste into something safe to store or repurpose, potentially reclaiming nutrients for the agricultural systems described in a later chapter, or dedicate stable, sealed storage volume to material that cannot simply be discarded outside without contaminating a surface that later research or agriculture might depend on staying uncontaminated. This is not a dramatic risk in the way a pressure failure is. It is, instead, a slow, compounding logistics and public health problem, hidden behind a bathroom door that a permanent settlement has to solve continuously and correctly for exactly as long as anyone lives there, with no municipal system quietly absorbing the failure modes the way one does on Earth. All 3 systems sound almost mundane described this way. All 3 are absolutely required, every hour, for the room in the opening to remain the room in the opening rather than something considerably more dangerous. The coupling matters because failures in engineered systems rarely stay where they start. A power interruption is not merely a power interruption. It is also, within minutes, a thermal control interruption, because pumps and fans stop moving air and coolant. A thermal control failure is not merely a comfort problem. If it runs long enough in the wrong direction, it becomes a condensation problem, then a corrosion problem, then, eventually, an electronics problem in systems that were never rated for the humidity now sitting inside their housings. A water recovery failure is not merely a hygiene inconvenience. The same loop that reclaims wash water is frequently integrated with humidity control, so a failure there can cascade into the same thermal and electrical exposure. None of these connections are exotic engineering surprises. They are the ordinary, well-understood behavior of any tightly coupled life support architecture. The same behavior spacecraft designers have studied for decades on missions where a single fault, left unmanaged, does not stay single. Walk one plausible sequence through from beginning to end, because the abstract description of coupling is easier to trust once it has a concrete shape. A pump circulating coolant through the thermal control loop develops a worn bearing and fails during the Martian night, when temperatures outside have already dropped furthest from anything survivable. Within minutes, without active circulation, heat generated by onboard electronics, the same electronics running the oxygen generator and the CO2 scrubber, begins accumulating faster than it can radiate away through the now static loop. As internal temperatures climb, several pieces of hardware not directly related to thermal control at all begin operating outside their rated range, including, in a plausible worst case, control electronics for the backup pump meant to cover exactly this failure, if that backup was already degraded, worn by the same dust and years of operation described in later chapters. The redundancy the design counted on may not fully engage, or may engage at reduced capacity right when full capacity is needed most. None of this requires a single dramatic malfunction. It requires one ordinary bearing, worn past tolerance, at an inconvenient hour, interacting with a system whose backup was never quite as fresh as the day it was installed. This is not a hypothetical invented for dramatic effect. It is the standard failure mode reasoning engineers already use when designing any tightly coupled life support architecture on spacecraft as much as on Mars. This is where the comfortable word redundancy starts to need a harder look. Every serious habitat design includes backup systems, a second oxygen generator, a second pump, a second power bus. That is real, and it matters, and later chapters give real credit to the engineering solutions built to survive exactly this problem. Redundancy answers the question, what happens if this part fails? It does not answer the much harder question, what happens if this part fails while the part meant to replace it is also degraded, or in use elsewhere, or waiting on a repair that cannot happen for another 11 months? A backup system is not permanent protection. It is a second chance, consumed the moment it activates, and a home. Unlike a mission, has to keep having second chances indefinitely, for years that stretch into decades, without ever being allowed to run out. Redundancy appears to make the chain safe until replacement and repair are included. There is a further wrinkle worth naming before moving on, because it changes how a resident would actually have to live inside this chain rather than merely design it. A coupled system does not just propagate failure outward through its own hardware. It also propagates constraint into human behavior. If a backup oxygen generator is currently the only working oxygen generator because its primary counterpart is offline for maintenance, then decisions that would otherwise be routine, how many people can safely be in the airlock at once? How strenuous a work shift can be scheduled? Whether a second, unrelated system can be taken offline for its own scheduled maintenance at the same time. All become constrained by a single point of failure that used to be invisible precisely because it had a partner covering for it. On Earth, a furnace with a broken backup circulator simply runs a little less efficiently until someone visits with a replacement part. Inside a coupled Martian life support chain, the same kind of ordinary, unremarkable degradation can quietly narrow the list of decisions a crew is allowed to make days or weeks before anyone would describe the situation as an emergency. On Earth, when a furnace fails in the middle of winter, the household's actual emergency plan is rarely dramatic. A phone call, a technician's visit, same day if the household is fortunate, and a repair, usually completed with parts pulled from a regional supply network built up over more than a century of industrial infrastructure nobody in the house had to build themselves. If the part genuinely cannot be sourced locally, It ships overnight from a warehouse a few hundred kilometers away. The entire transaction, from failure to fix, typically resolves in days. This is so unremarkable that it barely registers as infrastructure at all. It is simply what happens when something breaks. None of that transaction exists on Mars, and the reason is not incompetence or underinvestment. It is orbital mechanics. Earth and Mars line up for an efficient, minimum energy transfer window roughly once every 26 months, and a one-way transit along that trajectory takes the better part of a year. Outside that window, sending anything. A replacement pump, a spare valve, a technician, becomes dramatically more expensive in fuel and time, and during much of the orbital cycle, the two planets are also separated by enough distance that even a radio message takes between 4 and 24 minutes to arrive one way, ruling out real-time troubleshooting with Earth-based engineers for a large fraction of any given year. A part that fails today does not get replaced next week. In the worst timing, it does not get replaced for the better part of 2 years. And even in the best timing, help is coming means help arriving in months, not hours. It is worth sitting with why this timing works the way it does, because it is orbital geometry, not a limitation anyone chose. Earth completes an orbit around the Sun in a year. Mars takes roughly 1 year and 10 months. Because the two planets travel at different speeds along different-sized orbits, the distance between them swings dramatically, from as close as roughly 54 million kilometers at their nearest approach to well over 400 million kilometers when the Sun sits between them. The efficient, minimum fuel trajectories spacecraft actually use only become available when the geometry lines up correctly, which happens on a repeating roughly 26-month cycle. Outside that window, reaching Mars is not impossible, but it costs dramatically more propellant and time, the kind of expense that makes routine, as-needed resupply simply uneconomical at any foreseeable budget, and distance alone governs the radio problem. At the close end of that range, a one-way signal takes a little over 4 minutes. At the far end, it stretches past 20 minutes, meaning a single question and answer exchange with Earth-based engineers can, at the least convenient point in the cycle, before anyone has even begun discussing what to do about the fault itself. This is the fact that quietly reorganizes everything else in this film. An Earth home borrows an entire civilization's spare parts economy. Its factories, its warehouses, its overnight logistics networks, without anyone in the house ever having to think about where any of it comes from. A Martian home cannot borrow that economy at the timescale a genuine emergency requires. It has to carry a meaningful fraction of that economy inside itself. Spare components sized and stocked years in advance based on predicted failure rates, tools and diagnostic equipment sufficient to identify a fault without a specialist on a video call, 4 to 24 minutes delayed in each direction, and enough local manufacturing capability to produce at least some of what the original supply run did not anticipate needing. Every subsystem from Chapter 2 now implies a second, mostly invisible subsystem behind it. Not just the machine that provides air, but the sustained, self-contained capacity to keep that machine. Or something that does its job, running indefinitely without external resupply. The spare parts problem this creates is not simply a matter of packing more boxes onto the next resupply flight. It is a forecasting problem. And forecasting problems compound the further out they are asked to predict. A short mission can inventory its spares against a known, bounded set of failure modes accumulated from a limited number of operating hours. A permanent settlement has to forecast failure rates for equipment that, in many cases, has never actually operated continuously for the number of years the settlement plans to exist, meaning the inventory has to be sized against an estimate, not a track record. And every estimate carries the risk of being wrong in the one direction that matters, underestimating how many of a critical component will actually fail before the next resupply window opens. Overstock and the settlement wastes mass and launch cost on parts that sit unused. Understock, and the settlement discovers the gap in its estimate exactly when a life support system needs the part it does not have. Neither error is recoverable quickly, because the same 26-month cycle governing every other resupply question governs this one too. One mitigation strategy deserves mention here, because it represents the most direct engineering response to the resupply problem, even though it does not eliminate the underlying constraint. Mission planners have proposed pre-positioning strategies, where critical supplies, spare hardware, and even backup habitat modules are launched toward Mars well ahead of any crew, timed to arrive and be verified operational before anyone's survival depends on them, effectively front-loading a reserve large enough to absorb a longer stretch of bad luck than a single resupply cycle could otherwise guarantee. This is a genuinely sound engineering response, already incorporated into serious mission architectures, and it buys real margin. It does not, however, change the fundamental shape of the problem for a settlement intended to be permanent rather than mission length. A pre-positioned cache is still a finite cache. It reduces the frequency with which the 26-month resupply cycle becomes the binding constraint on survival. It does not remove that cycle from the equation, because no cache, however large, can be stocked against an indefinite future the way a continuously operating industry could be. A home that cannot call for help and receive it within a survivable timeframe is not automatically a failed home, but it is not the same category of home as one that can. Even on a day when both look, from the inside, equally comfortable, that distinction dormant on an ordinary Tuesday, decisive on the day something breaks, is the one worth carrying forward, because the next several chapters are about the machines engineers have proposed to make that distinction survivable, and about what those machines cost in return. Of everything Mars is missing, the missing magnetic field deserves to be understood on its own terms before it becomes a source of dread, because the actual mechanism is more interesting than the word radiation tends to allow. Earth's magnetic field is generated by convection in a molten iron outer core, a process still running on residual heat from the planet's formation more than 4.5 billion years ago. Mars had something similar once. Evidence of ancient, localized magnetization is still detectable in patches of its crust, but the planet's smaller size let its core cool, and its internal dynamo shut down, by most estimates, well over 3 billion years ago. What is left is a scatter of weak, localized magnetic patches, nowhere near strong enough or global enough to deflect the solar wind the way Earth's field does. Layer onto that an atmosphere providing only a small fraction of Earth's shielding mass overhead, and the surface of Mars receives a steady, largely unfiltered dose of galactic cosmic radiation, supplemented by occasional spikes from solar particle events. Instruments on the Curiosity rover have measured this directly, not estimated it from theory. A surface dose rate in the neighborhood of 0.7 of a millisievert per day. Multiplied across a year, that works out to roughly 250 millisieverts. For comparison, background radiation on Earth's surface runs at only 2 to 3 millisieverts annually, meaning a year on the Martian surface delivers on the order of 100 times the ambient dose a person absorbs living at sea level on Earth. It is worth being exact about what that number does and does not mean. It is not an acutely lethal dose. The threshold for acute radiation sickness sits several thousand times higher, in the range of several sieverts delivered in a short period. What a sustained Martian dose actually does is accumulate, elevating long-term cancer risk, and raising concern about damage to the central nervous system with prolonged exposure. The kind of harm that shows up in a statistic a decade later, not a symptom the same afternoon. A comparison helps make a number like 0.7 of a millisievert concrete. A single chest X-ray delivers a dose in roughly that same range, meaning an unshielded day on the Martian surface is, very approximately, comparable to receiving a chest X-ray's worth of radiation, repeated every day, for years, without pause, and without the recovery time between exposures that makes a single medical scan an acceptable, ordinary risk, real, serious, and worth solving. Not, contrary to a common exaggeration, an environment that cooks a person in the open air. Because that risk accumulates rather than strikes all at once, it is managed the same way accumulated occupational exposure is managed on Earth, by tracking it individually, not just estimating it at the population level. Astronauts on current missions already wear personal dosimeters that log radiation exposure continuously, and mission planners track each individual's cumulative career dose against established limits, adjusting future assignments once someone approaches theirs. A Martian settlement would need the same discipline extended indefinitely rather than across a single mission. Continuous personal monitoring, transparent record keeping, and a willingness to rotate people away from higher exposure duties, such as surface excursions or exterior maintenance work. Once their measured lifetime dose reached a threshold, the settlement's medical staff considered responsible. That kind of bookkeeping does not reduce the underlying radiation environment. It is simply the ordinary, unglamorous discipline that keeps a known, accumulating risk from becoming an unmanaged one. The magnetic field itself deserves a moment of its own history, because Mars lost its magnetic field tends to get repeated as a fact without the mechanism behind it. Early in the planet's life, evidence embedded in patches of its ancient crust shows a global field once existed, generated the same way Earth still is, heat-driven convection in a molten metallic core. Mars is smaller than Earth, with less internal heat and a thinner mantle insulating that heat, and its core appears to have cooled past the point of sustaining large-scale convection sometime before the planet reached even 1.5 billion years of age. Well over 3 billion years before the present. What remains is not nothing. Isolated regions of the crust, magnetized while the field still ran, retain patches of local magnetism, strong enough for orbiting instruments to detect. But scattered crustal patches are not a global shield. They cover a fraction of the surface, and even where they exist, their strength falls far short of what would be needed to meaningfully redirect incoming radiation the way Earth's coherent, planet-spanning field does. The dynamo did not weaken. It stopped, and nothing has restarted it since. It also matters to separate two distinct kinds of radiation exposure that get flattened together too often because they demand different responses. The steady 0.7 of a millisievert per day comes primarily from galactic cosmic rays, a more or less constant background flux arriving from outside the solar system, the kind of chronic, low-level exposure that accumulates gradually and mainly threatens long-term health. Solar particle events are a different animal entirely. Sudden, intense bursts of energetic particles thrown off by solar flares and coronal mass ejections, capable of delivering a dangerous dose in a matter of hours rather than years. Though, unlike the constant background, they are also, in principle, detectable in advance and survivable with the right response. Spacecraft and orbital stations already maintain storm shelter procedures for exactly this scenario. A smaller, more heavily shielded compartment where a crew can wait out the hours or days of an acute solar event under the additional mass of water tanks, equipment, or dedicated shielding material rather than staying exposed in a less protected part of the habitat. A Martian home would need the same capability, permanently available, on top of the steady day-to-day shielding already discussed. One more system, on top of the ones already listed, that has to work correctly the one day it is genuinely needed. And here the engineering case genuinely earns some optimism. Shielding against this kind of radiation is not a fantasy technology. It follows well-understood physics, and several approaches have real, demonstrated grounding. Piling regolith, the loose Martian soil, and crushed rock covering the surface over a habitat provides meaningful attenuation in the first 15 to 20 centimeters of depth, with the shielding effect improving further if that regolith happens to be hydrogen-rich, since hydrogen nuclei are unusually effective at scattering the high-energy particles involved. Water offers the same advantage more efficiently pound for pound, which is part of why habitat designs sometimes propose wrapping crew quarters in water tanks, doing double duty as both a life support reserve and a shield. Most striking of all are Mars's lava tubes, underground volcanic caverns, some mapped at widths exceeding 400 meters, left behind by ancient volcanic activity. Experiments conducted inside comparable lava tube caves on Earth have measured radiation reductions of roughly 80% compared to the surface immediately overhead. Orbital imagery has already catalogued well over 1,000 candidate tube openings across the Martian surface. None of this is speculative science fiction. It is physics that already works, on Earth, in caves that already exist, applied to a planet that appears to have thousands of comparable structures waiting. Every one of these shielding strategies also carries an economic dimension worth naming, because mass is the currency that governs almost every decision in spaceflight, and shielding is, fundamentally, a mass problem. Launching material from Earth to Mars is extraordinarily expensive per kilogram, which is precisely why regolith and lava tube strategies are so attractive in the first place. They use mass that is already on Mars, free of any launch cost, rather than mass that has to be lifted out of Earth's gravity, and transported across tens of millions of kilometers. A habitat design that instead tried to ship enough dense shielding material from Earth to match what a lava tube or a thick regolith covering provides, for free, would face a launch mass penalty large enough to be effectively prohibitive at any realistic budget. This is part of why in-situ approaches dominate serious engineering proposals, not only because they work physically, but because they are the only shielding strategy whose cost does not scale directly with the price of launching mass off one planet and landing it safely on another. None of these approaches has been built and proven at the scale a real settlement would need. That qualification matters, and this film will not let it quietly disappear. But the underlying case is genuinely strong. Shielding the human body from Martian radiation is, by the standards of engineering problems, a solvable one. Every layer of protection still has to be built before it can be tested against Mars. So follow the case one layer further, into the resources a home would need to stop depending on Earth at all. If a Martian home could eventually stop needing anything shipped from Earth, water, oxygen, food, the entire calculation this film has been building would change, because the crushing cost of resupply across a distance measured in months would simply stop applying. This is, without exaggeration, the most hopeful idea available to anyone designing a permanent settlement, and it deserves to be presented as convincingly as the evidence actually allows before anything complicates it. Start with water, because the news here is genuinely good. Orbital missions have found it in real abundance. Mars Odyssey detected subsurface water ice in quantities researchers described as sufficient to fill Lake Michigan twice over, distributed across substantial portions of the mid-latitudes and poles. The Phoenix lander confirmed the presence of that ice directly, digging into it near the northern polar region in 2008. The Mars Reconnaissance Orbiter later identified exposed ice sheets on steep slopes at several sites, some remarkably close to the surface. Additional water exists locked inside hydrated minerals scattered across the planet. This is not a trace resource. It is a real, mappable reserve. And it is the foundation every serious in-situ resource proposal builds on. Extracting it is where the optimism has to get more careful. Pure ice can be processed at relatively modest temperatures, but much of the water bound in hydrated minerals requires heating to roughly 300 degrees Celsius to release, and many of the accessible deposits are contaminated with perchlorate compounds. Chemically useful in some contexts, toxic in drinking water, requiring additional purification before use. None of that is disqualifying. It simply means there is water, and there is a working extraction industry are different claims, separated by hardware that has been tested in simulation and small-scale prototype, not yet deployed and operated on Mars itself. Oxygen tells a similar story on a shorter timeline. In situ resource utilization concepts that pull oxygen directly from the carbon dioxide, rich Martian atmosphere have moved from theory into demonstrated hardware. Small-scale experiments have already shown that atmospheric processing can generate usable oxygen under real Martian conditions, a genuine proof of concept for technology that could, in principle, scale towards supporting both breathing and rocket propellant production. The clearest example of this arrived not in a lab on Earth but on the Martian surface itself, an experimental instrument riding aboard NASA's Perseverance rover, roughly the size of a car battery, spent much of the early 2020 seconds repeatedly converting Martian atmospheric carbon dioxide into breathable oxygen, run after run, under the planet's actual temperature, pressure, and dust conditions rather than a simulated approximation of them. It produced oxygen in small quantities, enough to validate the chemistry and the hardware, not enough to supply a settlement. But the distinction between this works in theory and this has already worked, repeatedly, in the actual environment it would need to operate in, is exactly the distinction that separates a hopeful idea from a demonstrated one. Scaling it from a car battery-sized demonstration unit to a supply sufficient for a permanent population is the part still ahead of the engineering, not behind it. Nutrition, and not merely calorie count, is the harder half of the food question, worth separating out explicitly. A closed-loop system does not just have to produce enough mass of edible material to meet a population's energy needs. It has to produce a nutritionally complete diet, the right balance of protein, essential fatty acids, vitamins, and minerals a human body requires to function over years, not just enough food to avoid hunger in the short term. Controlled environment agriculture has demonstrated real success growing a narrow range of crops well suited to sealed, artificially lit conditions. Leafy greens and certain vegetables chief among them, but a genuinely complete diet draws on a much wider range of crop types, some of which grow far less efficiently or have not yet been seriously tested under the specific light, atmosphere, and gravity conditions a Martian greenhouse would provide. Producing enough calories to survive and producing a diet a body can remain healthy on indefinitely are related problems. But they are not the same problem, and Martian food research has made considerably more progress on the first than on the second. Food closes the loop, and it is here that the most honest caution belongs. Controlled environment agriculture has real, documented wins. NASA's Advanced Plant Habitat sustained a crop of edible chili peppers through a full growing cycle aboard the International Space Station, the longest continuous edible crop growth ever achieved in orbit. That is a genuine achievement. Full automation, sealed environment, real food at the end of it. It is also, by necessity, closet scale. A single experimental chamber producing a garnish, not a harvest. No closed-loop agricultural system anywhere has ever sustained a human population without external input at anything resembling colony scale. The most ambitious attempt at true closed-loop living. Biosphere 2, an 8-person sealed ecosystem built on Earth in the early 1990s, with soil, plants, and an atmosphere designed to balance itself, collapsed within roughly 2 years. Oxygen levels fell further than predicted. Pests spread unchecked through the crops, and the microbial community in the composting soil never reached the equilibrium the design assumed it would. What makes Biosphere 2 worth returning to, rather than treating as a single cautionary anecdote, is how ordinary its individual failure points actually were. Nobody involved lacked expertise. The project assembled genuine ecologists, agronomists, and engineers, working with a budget and a level of ambition far beyond anything a small Martian outpost would attempt in its early years. The failure was not a single dramatic event, but an accumulation of small miscalculations in a system too complex for anyone to fully model in advance. Soil microbes consuming more oxygen than predicted, insect populations finding an ecological niche nobody had planned for, crop yields falling short of the calorie targets the closed system needed to balance. Every one of those miscalculations, individually, sounds survivable. Together, compounding over months inside a sealed structure with no outside atmosphere to buffer the error, they were not. A Martian food system carries the same structural risk, magnified by an environment with even less room for miscalculation than a biosphere. 2 inches the Arizona desert, where, unlike Mars, a genuine outside atmosphere sat only a door away. None of this erases the underlying hope. Water exists in abundance. Oxygen extraction has already been demonstrated on the Martian surface. Food production at small scale has been proven in orbit. Every individual piece of a self-sufficient Martian home has, in some form, already worked. What has never been demonstrated is all of it, running together, continuously, at the scale a real population requires. And the recycling systems tying it together carry their own quiet limitation. The International Space Station's water recovery system, one of the most refined closed-loop systems ever operated by humans, reclaims somewhere between 90 and 98% of the water that passes through it. That is a remarkable engineering achievement. It is also, by definition, not 100%. 2 to 10% of the water in the loop is lost with every cycle. To processing inefficiency, to material that cannot be recovered, to the ordinary entropy of any real machine. And every fraction of that loss has to be replaced by something. It is worth understanding, briefly, why that last small percentage is so much harder to recover than the rest, because it explains why 98% is a genuine engineering triumph and still not the finish line. Most of the water passing through a system, like the ISS's water recovery loop, is recovered through relatively straightforward distillation and filtration. What remains afterward is a concentrated brine, the leftover mixture of salts, minerals, and contaminants too concentrated for standard filtration to process efficiently. Reclaiming water from that brine requires additional, more specialized hardware, sometimes called a brine processor, running a slower and more energy-intensive process to squeeze out the water still locked inside it. Each additional percentage point of recovery costs disproportionately more equipment, more energy, and more maintenance than the percentage point before it. The easy water comes out first, and the hardest, most expensive water is exactly the water that determines whether the loop closes completely or leaves a gap someone has to fill from outside. On a mission measured in months, that residual loss is a manageable inconvenience covered by an Earth-launched reserve. On a home measured in decades, it becomes a standing bill that never stops arriving. Every layer of protection adds another system that must work for years without an ordinary supply chain. Step back from the systems for a moment and consider the ground they stand on, because Mars does not need a dramatic event to start collecting on the bill built up across the last 3 chapters. It only needs dust, and it has an extraordinary amount of it. Martian dust grains typically measure somewhere between 20 and 150 microns across, fine enough that some of the smallest particles rival cigarette smoke in scale, and billions of years of impact weathering have left them jagged and angular rather than smooth. That shape is the operative detail. This is not sand in the sense a beach uses the word, rounded by water and wind into something relatively gentle. It is closer, mechanically, to microscopic broken glass, distributed across the entire surface of the planet, in a layer that storms lift and redeposit continuously. The evidence for what this does to hardware is not theoretical. It is sitting in mission logs going back 2 decades. The solar-powered rovers Spirit and Opportunity both tracked measurable power loss as dust settled onto their panels over time. Spirit lost power at a documented rate of roughly 0.77% per Martian day. Opportunity, a little over half that, a slow, compounding tax on every watt the mission depended on. Periodic wind events occasionally cleared some of that accumulation, buying the rovers unplanned extensions to their working lives. But the underlying mechanism never stopped. Dust falls, dust reduces output, and nothing about the process asks permission first. The clearest demonstration of what happens when that slow accumulation turns suddenly arrived in 2018, when a dust storm grew to encircle the entire planet, thickening the atmosphere with suspended particles severely enough to block sunlight from reaching Opportunity's solar panels. The rover, which had already outlasted its original 90-day mission by more than 14 years, sent its last transmission as the storm darkened its skies and never reported back. A single atmospheric event, not a mechanical breakdown, ended a mission that had survived everything else Mars had thrown at it for a decade and a half. A habitat's power architecture has to be designed with exactly that scenario in mind. Not the routine accumulation Spirit and Opportunity track day to day, but the planet-scale event capable of removing solar generation almost entirely for weeks at a time. The Sojourner rover, decades earlier, documented a second and less obvious effect. Contact between dust and moving wheels generated measurable electrostatic charge through simple friction, a phenomenon engineers call tribocharging. During larger dust events, that same mechanism has been associated with static discharges, substantial enough to threaten sensitive electronics. Dust storm behavior on Mars also follows a seasonal rhythm worth understanding, because it turns an abstract hazard into a predictable planning problem rather than a random one. Regional storms, smaller, more localized events occur with some frequency across the Martian year. But the largest, planet-encircling storms tend to cluster around the period when Mars is closest to the Sun in its elliptical orbit, when surface heating is at its most intense and best able to loft dust into the atmosphere at scale. This seasonal clustering means a settlement's power and maintenance planning is not guessing blindly. Mission planners can anticipate a higher risk window each Martian year and schedule critical maintenance, stockpile reserve power, and avoid dust-sensitive operations accordingly. That predictability is a genuine asset. It does not remove the hazard. It only tells a settlement, with reasonable confidence, which weeks of its calendar deserve the least tolerance for anything else going wrong at the same time. The part of this story that matters most for a permanent home, though, is not the dramatic discharge. It is the ordinary wear. Every rover mission to Mars has required specifically engineered seals, typically spring-loaded assemblies built from wear-resistant materials like PTFE, specifically to keep fine dust out of joints, gears, and bearings, because unprotected, that abrasive grit works its way into precisely the places where two moving surfaces meet and grinds against them like sandpaper with every cycle. The problem extends beyond stationary hardware to anything a resident actually wears outside the habitat. A pressurized suit is, at every joint, shoulder, hip, knee, glove, precisely the kind of moving mechanical interface dust is most effective at degrading. And unlike a rover's joints, a suit's joints have to keep working reliably enough to protect a human life inside them every single time someone steps outside to perform maintenance, collect samples, or simply walk to another structure. Airlocks compound the exposure. Every return trip through one carries dust back inside on the suit's exterior, however carefully residents try to brush it off first, meaning the dust problem is never fully confined to the outside world, the way the pressure boundary itself is. A permanent settlement does not get to treat dust as an occasional field hazard encountered on excursions. It is a substance the habitat's interior slowly, unavoidably accumulates, one airlock cycle at a time, for as long as anyone keeps going outside. This is not a design flaw anyone failed to anticipate. Engineers have understood and accounted for it for decades, which is itself the point worth sitting with. Dust resistance is not an afterthought bolted onto Martian hardware. It is baked into the baseline requirements, because without it, ordinary mechanical wear accelerates to the point of failure far faster than the same components would fail on Earth. Now connect this back to everything built across the last 2 chapters. The radiation shielding from Chapter 4, if it involves any moving components, vents, access hatches, mechanical louvers regulating airflow through a regolith or water shield, sits exposed to this same abrasive environment. The oxygen extraction and water recovery hardware from Chapter 5, wherever it interfaces with the outside world through intakes, pumps, or seals, sits exposed to it as well. None of this hardware was designed in a vacuum, so to speak. Engineers already know to armor against dust, but every additional system a home adds, every layer of protection, every closed loop, is also one more surface for that fine, jagged, electrostatically charged material to slowly, patiently degrade. Engineers are not simply accepting this attrition as an unavoidable cost, and it is worth crediting the countermeasures already in development rather than treating dust as a purely unsolved threat. Electrodynamic dust shield technology, tested in NASA laboratories, uses an electrode pattern embedded beneath a panel surface to generate a traveling electric field that lifts and sweeps accumulated dust away without any moving parts or water, offering a way to keep solar arrays and optical surfaces clear without the maintenance burden a mechanical wiper would introduce. Robotic and vibration-based cleaning systems have also been proposed and tested at smaller scales. None of these approaches has yet been deployed at the scale a full settlement solar array or set of external sensors would require, and each adds its own layer of hardware, with its own failure modes, its own power draw, its own eventual wear. To a system that was already accumulating complexity in earlier chapters, progress against dust is real. It is not the same claim as dust being solved. Mars does not have to attack a home directly to win a long war of attrition against it. It only has to be persistently, mechanically present at a scale measured in geological time against machinery that has to keep working on a human timescale instead. Degradation is survivable if someone can always repair it. So the next question is who that someone actually is, and what happens when repair itself starts running out of options. Picture the failure this film has been building towards since Chapter 3. A critical part, a valve, a pump seal, a circuit board controlling one of the 6 coupled life support systems, finally wears past its tolerance and fails, exactly as the last chapter predicted it eventually would. On Earth, this triggers an unremarkable sequence. Identify the part, order it, receive it within days, replace it. On Mars, the same failure triggers a genuinely different question, because none of the 3 steps in that sequence are available on the same timescale. There is no local factory, there is no regional warehouse, and depending on where the 2 planets currently sit in their orbits, there may not even be a fast way to ask Earth for help. A one-way radio message alone can take between 4 and 24 minutes to arrive, ruling out real-time troubleshooting for a meaningful fraction of any given year, before the months-long question of physically shipping a replacement even enters the conversation. The honest engineering response to this problem is local manufacturing, and, as with radiation shielding, the real progress here deserves genuine credit before its limits get named. 3-dimensional printing has already been demonstrated functionally aboard the International Space Station since 2014, producing plastic tools and components on demand rather than waiting on a resupply flight. In 2024, the European Space Agency successfully demonstrated metal 3-dimensional printing in orbit for the first time, a meaningful step beyond plastic parts towards structural and mechanical components. On the ground, researchers have already produced prototype construction material from simulated Martian regolith, opening a real path toward building habitat structures from local soil rather than shipping every wall panel from Earth. The honest limit sits right next to that progress. Printing a structural bracket or a length of habitat wall from local material is a genuinely different problem from manufacturing a precision valve seal, a semiconductor, or an electronic control board. the kind of high-tolerance, materials-intensive components that make up a meaningful share of any life support system's most failure-prone parts. Current in-situ resource studies are candid about this gap. Most of the processes under active investigation have only reached proof-of-concept demonstration in terrestrial laboratories and still require testing under the specific conditions of the Martian environment. Its gravity, its temperature swings, its near vacuum, before anyone can be confident they will perform identically away from Earth. Rare and specialized materials, refined metals, and precision electronics remain for the foreseeable future, dependent on what ships from Earth once every 26 months. Engineers have a term for the statistic that governs exactly this problem. Mean time between failures, a measure of how long, on average, a given piece of equipment runs before it breaks down. Every component in a Martian life support system has one, whether or not anyone has precisely measured it yet, and the entire architecture of spare parts, maintenance schedules, and local manufacturing capability exists to answer a single question derived from that statistic. Across the full inventory of everything the habitat depends on, how often, on average, does something fail, and does the settlement's repair capacity meet or exceed that rate? A short mission only has to outrun the failure rate for the length of the mission. A permanent home has to outrun it forever, which means the repair capacity has to scale to match not a fixed number of failures, but an open-ended, continuously arriving stream of them for as long as anyone intends to keep living there. This is the point where a repair economy built for a short mission and a repair economy built for a permanent home genuinely diverge, rather than merely differing in degree. A short mission can carry a calculated set of spare parts sized to its known duration and accept the small residual risk that something unanticipated breaks anyway. An acceptable gamble over months. A home cannot make that same bet over decades, because the list of things that could eventually fail, given enough time, eventually includes nearly everything. Absent a genuine local industry capable of producing an expanding range of replacement components, a permanent settlement is not solving its maintenance problem. It is deferring it, one 26-month resupply cycle at a time, and hoping nothing important breaks in a window when nothing can be sent. This constraint reshapes who a settlement actually needs living inside it, not just what it needs stocked in a storage bay. On Earth, a complex facility relies on a deep bench of narrow specialists, one engineer for the water system, another for the electrical grid, a separate technician entirely for structural repairs, each backed by decades of specific training and, when their own knowledge runs out, a phone call to someone else's. A settlement that cannot call a specialist and cannot wait months for one to arrive needs the opposite profile. Generalists capable of diagnosing and repairing across multiple overlapping systems, cross-trained deliberately so that the loss of any single person to illness, injury, or simple unavailability does not also mean the loss of the only person who understood a given system. That requirement filters who can realistically live there almost as strictly as the physiological and psychological demands covered later in this film. Not everyone capable of surviving Mars physically is equally capable of being one of the small number of people a settlement needs to keep it running indefinitely. What actually accumulates in that deferral is not a single dramatic breakdown, but a series of smaller compromises. A redundant system pressed into permanent primary duty because its counterpart cannot be repaired. A workaround jury-rigged from parts meant for something else, quietly reducing the margin available the next time something goes wrong. A maintenance schedule stretched further than its design tolerated because the technician capable of the repair is occupied elsewhere, or the part on hand is the wrong one. None of these compromises look like a crisis in isolation. Stacked together, over years, they are exactly how the margin for error in Chapter 2's coupled systems quietly disappears. Not through one dramatic failure, but through the slow erosion of the safety net standing behind every failure that came before it. The material science behind local manufacturing deserves a slightly closer look, because print it from regolith tends to get repeated as though it were already a solved problem rather than an active research question. Martian regolith is not, on its own, a ready construction material. Loose, dry soil lacks the binding properties concrete needs to hold structural load. Researchers working with regolith simulants, Earth-made material formulated to match the mineral composition measured on Mars, have tested various approaches to solving this, including mixing the simulant with polymer binders and, in some experimental work, with sulfur, which can be melted and used as a natural cementing agent once cooled, since sulfur exists in Martian soil in usable quantities and does not require water the way ordinary Earth concrete does. Early results show real promise. Printed and sulfur-bound regolith samples have demonstrated compressive strength competitive with ordinary construction concrete in laboratory testing. What has not yet happened is testing that same process using actual Martian regolith under actual Martian gravity, temperature, and near-vacuum conditions at the scale of an actual habitat wall rather than a laboratory sample. The chemistry is promising. The proof under real conditions is still ahead. That distinction between laboratory success and field-proven reliability recurs across nearly every technology this film has credited so far, and it deserves to be named once, plainly as a pattern rather than left scattered across individual chapters. Earth-based laboratories can approximate several aspects of the Martian environment simultaneously. Vacuum chambers replicate the pressure, cold chambers replicate the temperature, regolith simulants replicate the mineral composition of the soil, but no facility on Earth replicates all of them together, continuously, for years, while also replicating Mars's specific gravity, its radiation environment, and its dust. Each individual test therefore validates a piece of the puzzle under conditions chosen to isolate that piece, which is good scientific practice and also, unavoidably, an approximation. The habitat, the shielding, the water and oxygen extraction, and the manufacturing capability described across this film have each cleared meaningful, real hurdles in exactly this piecemeal way. None of them has yet been tested as a single, integrated system operating on the actual planet for the length of time a genuine home would require. That gap between piece-by-piece validation and integrated, real-world proof is not a criticism of the engineering. It is simply the honest distance still remaining between where the technology currently stands and where a settlement would need it to be. Even a perfectly maintained machine would not remove Mars from the human body. Suppose for a moment that every problem in the previous 7 chapters is solved. The pressure vessel holds. The 6 coupled systems run without interruption. The dust never wins. The parts never run out. It is worth pausing here, deliberately, because this is the version of the story that optimistic accounts of Martian settlement tend to stop at. A fully functioning habitat, indefinitely maintained, problem solved. It is not the end of the story. Even inside a habitat that never fails, Mars still reaches the human body in at least 2 ways. No amount of engineering, on current evidence, fully removes. The first is radiation. And Chapter 4 already established the honest shape of that risk. Not acutely lethal, but a steady accumulation that raises long-term cancer risk and raises concern about damage to the central nervous system. The longer exposure continues. Shielding reduces that dose. Meaningfully, if built at the scale a lava tube or a thick regolith covering allows. But reduction is not elimination. Every square meter of a settlement's surface infrastructure, every window, every airlock, every moment spent outside a fully shielded core performing maintenance or exploration reopens a small amount of that exposure. A body living permanently within Martian shielding still absorbs more radiation across a lifetime than the same body would have absorbed staying on Earth. The engineering in Chapter 4 buys a meaningful reduction. It does not buy Earth's number. The second is gravity. And this is where the honest account gets genuinely harder to deliver, because it requires resisting the pull toward a tidy answer in either direction. Mars's surface gravity measures 3.72 meters per second squared, about 38% of Earth's. What happens to a human body at zero gravity, sustained for months, is extensively documented from decades of research aboard orbital stations. Bone density loss on the order of 1 to 2% per month in weight-bearing bones. Muscle mass loss reaching as high as 30% on the longest missions, and significant redistribution of bodily fluids toward the head and chest. With cardiovascular and vision effects that researchers are still characterizing, that evidence is real, extensive, and well established. What does not exist anywhere in the human research record is equivalent long-term data for gravity that is neither zero nor Earth normal, the specific condition of living at 38%. For years rather than weeks, countermeasures developed for zero gravity offer a partial, imperfect precedent for how a Martian home might try to close this gap in practice, even without direct partial gravity data to validate them. Astronauts on long-duration orbital missions already follow a demanding daily exercise regimen, typically well over an hour of resistance and cardiovascular training, using equipment specifically engineered to simulate load-bearing stress the body would otherwise lack in weightlessness. And that regimen measurably slows, though does not eliminate, the bone and muscle loss documented across those missions. A Martian settlement would very likely adopt a comparable protocol, scaled down proportionally under the assumption that 38% gravity requires less compensatory loading than zero gravity does. That assumption is reasonable. It is also, on the current evidence, unverified. Nobody has measured how much exercise is actually sufficient to offset deconditioning at exactly this gravitational level, which means any Martian countermeasure program would, in its early years, be operating on an educated estimate rather than a validated protocol, adjusted in real time as the first residents' own bodies became the first real data. This gap is not a minor omission waiting to be filled by an obvious extrapolation. It is close to a complete absence. The only humans who have ever lived under any level of reduced but non-zero gravity are the 12 Apollo astronauts who walked on the moon at 1/6 of Earth's gravity, and none of them remained there longer than about 3 days. A systematic review of the available research literature on partial gravity biomechanics and cardiopulmonary response identified 43 relevant peer-reviewed studies. Not one examined long-term human exposure. What informs current thinking instead is a chain of inference. Extrapolation from zero-gravity data, short-duration lunar experience, ground-based simulations, and animal studies in specially built partial gravity research platforms. Each individually useful, none of them a direct substitute for the thing itself. The most recent simulation-based research suggests that gravity below roughly 40% of Earth's may sit under the threshold needed to fully maintain musculoskeletal and cardiovascular health over time, which would place Martian gravity uncomfortably close to a line nobody has actually crossed and measured. It is worth being clear about why this particular gap in the evidence has proven so hard to close. Rather than simply flagging it as an oversight, researchers have neglected to fill in. Studying long-term human response to zero gravity is possible because astronauts already spend months at a time aboard orbital stations for other operational reasons, generating a large, ethically uncomplicated dataset almost as a byproduct of ordinary spaceflight. No equivalent naturally occurring population exists for partial gravity. Nobody currently lives, works, or is stationed anywhere on Earth or in orbit at a sustained 38% of standard gravity. And building a facility capable of simulating it for months at a time, a large rotating structure, or an extended stay on the lunar surface, is itself a major undertaking that has not yet been funded or built at the scale long-term research would require. The absence of data here is not a research failure. It is a reflection of how genuinely difficult the underlying question is to study anywhere except the destination itself. The honest sentence here is not, Martian gravity is dangerous. It is, the evidence suggests Martian gravity is probably insufficient to fully prevent the kind of deconditioning well documented at zero gravity, and no human being has ever lived long enough at that exact gravitational level to confirm or refute the suggestion. That distinction matters enormously, and this film will not collapse it for the sake of a cleaner sentence. A genuinely unknown risk is not the same claim as a confirmed one, and treating the two identically, in either the alarmed direction or the falsely reassuring one, is exactly the kind of overclaim this account is built to avoid. There is a third, quieter physiological cost worth naming alongside radiation and gravity, because it does not announce itself as dramatically as either, but compounds across exactly the same timescale. A permanent home requires the fluid redistribution documented extensively in zero-gravity research, where bodily fluids that Earth's gravity ordinarily pulls toward the legs instead shift toward the head and chest, producing changes to vision and cardiovascular function that researchers have tracked closely across long-duration station missions. At Martian gravity again, partial rather than absent the honest position is the same one already established for bone and muscle. The effect is plausibly reduced compared to zero gravity, given that some downward pull remains. But by how much, and whether that reduction is sufficient to avoid the vision and cardiovascular changes seen in orbit, has not been directly measured in any human being for the same reason no long-term partial gravity population exists to measure. Every physiological question this chapter raises eventually arrives back at the same wall. Extensive zero-gravity data, extensive Earth gravity data, and a genuine, unresolved gap in between them, exactly where Mars sits. What both risks share, radiation and gravity alike, is the same underlying shape. They are not solved by the habitat working correctly. They are what remains once the habitat is working correctly. The cost of exchange between a body built by Earth's evolutionary history and a planet that offers only a partial, engineered substitute for the conditions that history assumed. Every system chronicled across the last 7 chapters exists to negotiate that exchange as favorably as physics allows. None of them, on current evidence, negotiates it away. The question is no longer whether people can remain alive there, but what conditions deserve to be called home. Change the register here, deliberately, because the chapters up to this point have been asking what a habitat and a body require. This one asks something different. What does it do to a person, and to the people around that person, to live permanently inside the answer? Earth already has a body of evidence on this, gathered not from Mars but from the closest analogues researchers have been able to build. NASA's HiCS program placed 6 volunteers inside a sealed, dome-shaped habitat on a Hawaiian volcano for 8 months, monitoring their interactions with wearable sensors that tracked proximity, movement, and vocal tone throughout the mission. What the data showed was a measurable decline in mood and a rise in interpersonal tension as the mission progressed, concentrated less at the beginning or the end than in the stretch through the middle, when the novelty of the situation had worn off but the return home still felt distant. Russia's Mars 500 program pushed the same basic question further, sealing 6 men inside a mock spacecraft in Moscow for 520 days. The length of a genuine round-trip Mars mission, and tracked a similar stage pattern of psychological adaptation, along with measurable shifts in stress-related hormones as the crew moved through distinct phases of the isolation. Long-duration Antarctic research stations, where crews of a dozen or more overwinter for 10 to 12 months cut off from easy evacuation, have documented a related and specifically named pattern researchers call the third quarter phenomenon. Not a steady decline, and not a crisis clustered near the beginning, but a psychological low point arriving roughly 3/4 of the way through the isolation period, when the ratio of time endured to time remaining feels most discouraging. These are not soft or anecdotal findings. They come from controlled, published, peer-reviewed research, and they describe a real and recurring pattern in how human beings respond to extended isolation and confinement. It would be a mistake, however, to treat them as a direct preview of Martian life, and the honest limitations are worth stating as plainly as the findings themselves. Every one of these analogues, without exception, lasted a matter of months to at most a couple of years. Nothing in the published research approaches the multi-decade, potentially generational timescale a genuine settlement implies. Every one of these analogues also preserved something Mars cannot offer: a real, if difficult, exit. High-seas participants knew that in a true emergency, the dome's door opened onto breathable Hawaiian air. Mars 500's volunteers knew, even sealed inside their mock spacecraft, that they remained in Moscow. Antarctic teams know that evacuation, while genuinely hard and weather-dependent, exists in the range of physical possibility. On Mars, that door does not open onto anything survivable, and the psychological weight of a truly permanent, physically inescapable situation, as opposed to a difficult but theoretically reversible one, is not something any Earth-based analogue has been able to test, because no ethical research design could impose it. Communication compounds the difference. High-seas simulated a 20-minute delay to mimic Mars, but a simulated delay a participant knows is artificial is not the same psychological experience as knowing, with total certainty, that the person on the other end of a message is never going to answer any faster for as long as either of them lives. The communication delay in particular deserves to be felt rather than only quoted as a number, because its psychological weight is easy to understate in the abstract. A message sent to a spouse, a parent, or a child back on Earth cannot be a conversation in any ordinary sense. It is closer to an exchange of letters, each one taking anywhere from roughly 8 minutes to nearly 50 minutes to travel round trip, depending on where the two planets currently sit in their orbits, with every reply already out of date by the time it arrives, describing a moment that has since moved on for whoever sent it. Ordinary relationship maintenance, the small, immediate reassurance of a quick call after a hard day, the ability to interrupt an argument before it compounds. The simple fact of hearing a familiar voice respond within seconds is not degraded on Mars. It is structurally unavailable, replaced by something closer to correspondence, indefinitely, for as long as the distance between the two planets remains what it is. The same repair economy logic explored earlier in this film for mechanical failure applies, with uncomfortable precision, to psychological ones. On Earth, a person struggling with the kind of mood decline or interpersonal conflict, the isolation research documents can, in principle, reach a therapist, a psychiatrist, a support network entirely separate from the people causing the stress in the first place, an outside resource arriving on a timescale of days rather than months. A small Martian settlement, at least in its early years, is unlikely to include a dedicated mental health professional among its handful of essential, cross-trained generalists, and even if it does, that single person is drawing from the same small, closed population as everyone else. With no colleague elsewhere to consult, and no ability to refer a difficult case somewhere better resourced, remote counseling with Earth-based professionals remains possible in the loosest sense, but it inherits the same communication delay just described. A therapeutic conversation stretched across minutes-long gaps in each direction is a fundamentally different tool than the same conversation held in real time. Psychological support, like every other system in this film, turns out to be something a home has to manufacture and maintain largely on its own, rather than something it can simply call in from outside when it is needed most. There is one more gap between the analogues and the real target worth naming plainly. because it is easy to miss under the weight of the psychological data itself. Every participant in High Seas, Mars 500, and the astronaut corps more broadly was selected, screened, and trained specifically for psychological resilience under confinement. A highly filtered population chosen in part because ordinary variation in temperament, conflict style, and stress tolerance was considered a mission risk worth engineering out in advance. A permanent settlement, if it is ever to be a home rather than a rotating outpost, eventually has to include people who were not selected that way. Engineers who happened to be difficult under pressure, children who did not apply for the psychological profile their parents were screened for, the ordinary range of temperament a real population contains, rather than the narrow band a selection committee approved. The isolation research describes how a hand-picked 6-person crew holds up. It says very little about how an unselected community would. Death itself raises a version of this same problem that isolation research rarely has to confront directly, because none of the analogues cited above have actually had to resolve it. Every Earth-based isolation study assumes, correctly, that if a participant dies or becomes critically ill beyond the facility's medical capability, evacuation, however difficult, remains a live option, and that the body of someone who does die can, eventually, be returned to family and to whatever burial or memorial tradition matters to them. Neither assumption holds on Mars in any straightforward way. A medical emergency beyond a settlement's on-site capability cannot be evacuated to Earth on any timescale that matters. The outcome has to be resolved with whatever people, equipment, and knowledge already exist inside the habitat, entirely alone, and a death on Mars raises a genuinely unresolved practical and cultural question, with no precedent to draw on. What happens to a body on a planet with no established custom, no existing infrastructure, and no return flight capable of bringing it home on any timescale a grieving family could reasonably wait for? None of the isolation research cited earlier in this chapter had to grapple with that question, because none of those studies were designed to. A permanent settlement eventually will. Layer onto all of this the question of children. Because if a Martian settlement is genuinely permanent rather than a rotating population of returning crews, it eventually has to answer whether people will be born and raised there. And this is the point in the film where the evidence runs out almost entirely. No human pregnancy has ever occurred in space, in any gravitational condition, let alone specifically in Martian gravity. What exists instead is a narrow body of animal research. Rodent studies conducted under microgravity have documented reduced birth rates, on the order of half the rate observed under normal gravity in some experiments, along with delayed fetal development and lower birth weights among offspring that were carried to term. That research describes zero gravity, not the 38% gravity Mars actually offers. And a scientific review published in 2023, examining human development and reproduction in space, stated the gap directly. The effects of altered gravity on reproductive function, from fetal development through puberty, have simply not been investigated at any partial gravity level. Not studied and found safe. Not studied and found dangerous. Not investigated. It would be a failure of the same honesty this film has tried to maintain throughout, to convert that absence into either a confident warning or a false reassurance. The correct sentence is the uncomfortable one. Nobody currently knows what Martian gravity would mean for a developing embryo, an infant's growing skeleton, or a child's cardiovascular system, as it forms under conditions no human child has ever experienced. And the corresponding research, for evident ethical reasons, cannot simply be run to find out. A first generation of children born on Mars would not be entering a home with a known safety profile in this specific dimension. They would be the first direct evidence anyone has ever gathered on the question, without having been able to give any form of consent to their role in gathering it. It is worth extending that thought one generation further, because the ethical weight of the gap does not end with a single birth. If early Martian children do grow up under Mars's gravity from infancy, Their skeletal and cardiovascular development would proceed under conditions their bodies never had an Earth-adapted baseline to compare against, unlike an adult settler whose bones and heart developed fully under Earth gravity before ever leaving it. Whether that difference would matter, whether a body built from conception onward at 38% gravity would develop into something well adapted to that environment, or would instead carry lifelong compounding disadvantages, or would land somewhere between those two outcomes, is not a question this film's evidence base can answer, and it should be treated with exactly the caution that absence of data demands. It is also a question a Martian settlement's second generation would not be answering hypothetically. They would simply be living it, as the first cohort of humans whose bodies actually resolve the question every prior chapter in this film has had to leave open. These pressures do not stay contained inside individual minds. They inevitably become questions of governance, because any group of people living permanently under shared, inescapable risk has to decide, explicitly or by default, who has authority when a life support decision and an interpersonal conflict arrive at the same time. Earth-based organizations operating in extreme environments, polar research stations, submarine crews, orbital station crews, typically resolve this with a clear command hierarchy, backed by the knowledge that serious disputes can eventually be escalated to, or removed by, an authority based on Earth. A permanent Martian settlement, especially as it grows beyond a small, hand-picked crew into something closer to a genuine town, does not have that same backstop available on any workable timescale. A dispute serious enough to require outside intervention still faces the same 24-minute and months-long resupply problem that governs every other request for help. Whatever governance structure emerges has to be robust enough to function entirely on local authority, resolving disputes, allocating scarce resources, and making decisions with life support stakes without the option every Earth-based extreme environment community has quietly relied on. The ability, in the worst case, to appeal to somewhere else. Population size compounds this problem in a way that is easy to overlook, because the earliest Martian settlements will almost certainly be small, a few dozen people at most, closer to HIC's or Mars 500's crew sizes than to a genuine town. Small, closed populations carry known social costs of their own. A limited pool of potential partners and friendships, repeated exposure to the same handful of personalities across every waking hour, with no ability to simply spend a day among strangers instead, and a scarcity of the kind of social variety that, on Earth, most people are free to seek out whenever a particular relationship or environment starts to feel exhausting. Small, isolated communities on Earth, from remote research outposts to island settlements, contend with versions of the same dynamic. What is unique to Mars is the combination. A small population, genuinely inescapable, expected to remain small for years before enough successful transport missions could meaningfully grow it, living under every other constraint this film has already described. Community scale is not a separate problem from the engineering and physiological ones. It is one more variable competing for the same, already stretched. Margin for error. None of this is presented to suggest that permanent settlement is impossible, or that the psychological and generational costs are necessarily catastrophic. The evidence does not support that conclusion either. And this film has tried not to overclaim in either direction from its opening line onward. What the evidence does support is a distinction that deserves to sit at the center of any honest account of Martian home life. The engineering chapters that came before this one describe risks that are well characterized, even where they remain only partially solved. Pressure, radiation, dust, maintenance, resupply. This chapter describes something categorically different. Not a known risk awaiting a better engineering solution, but a genuine absence of knowledge in exactly the two domains. Long-term psychological endurance without a real exit, and reproduction and childhood development under conditions no human has tested. That would matter most to a family actually trying to build a life there, rather than complete a mission and return. A home has to be a place a family can commit to across generations, not merely a place a crew can survive across a mission. And on the specific, evidence-based terms this chapter has laid out, that is the distinction Mars has not yet met. The question is no longer whether people can remain alive there, but what conditions deserve to be called home. Return, one last time, to the room from the opening. The air handler cycling on before anyone wakes, the glass of water that used to be someone's breath, the light rising on a timer built to imitate a day Mars does not provide, the warmth held against cold enough to be lethal in minutes, just beyond the wall. Nothing about that room has changed in the time it has taken to walk through 9 chapters of what stands behind it. What has changed is what the room can be honestly called. At the opening, that room looked like an ordinary domestic routine wearing an unfamiliar setting. Coffee, water, warmth, light, the same small comforts any house on Earth provides, just relocated. By now, the actual architecture underneath that resemblance has been traced in full. A pressure vessel holding back a surface where the atmosphere sits at 0.6% of Earth's, thin enough that unprotected fluids would boil rather than freeze. 6 coupled life support systems, standing in for a magnetic field, an atmosphere, a water cycle, and a biosphere that Mars simply does not supply. A resupply relationship stretched across a communication delay of up to 24 minutes, and a transfer window that opens only once every 26 months, shielding against a radiation dose roughly 100 times. Earth's background, built from genuinely sound engineering that has never been proven at settlement scale, water and oxygen extraction technologies that work in principle and in early demonstration, tied together by recycling loops that lose 2 to 10% of everything passing through them forever. An abrasive, electrostatically active dust that spends geological time wearing down whatever machinery stands in its way. A repair economy that has to manufacture its own future spare parts because the one that supplied its past parts is a year away. A body that tolerates Martian shielding rather than matching Martian conditions, still absorbing more radiation and less gravitational loading than it evolved for. And, underneath all of it, 2 genuine unknowns. Long-term psychological endurance with no real exit, and childhood development under conditions no human child has ever experienced. That no amount of engineering has resolved, because no amount of engineering can resolve an absence of evidence. None of that reclassifies the room as a trap. And this film has tried, deliberately, not to let nightmare do the explanatory work a word like that is tempted to do. Every single piece of that architecture is either already working in some demonstrated form, or resting on physics that genuinely supports it. The nightmare, if that word belongs anywhere in this account, is not a single catastrophe waiting to happen. It is the requirement that all of it, every coupled system, every shield, every recycling loop, every repair, keep working simultaneously, without interruption, for a length of time no mission has ever attempted, and no single failure is allowed to escape from. That requirement is exactly where the meaning of home has to be renegotiated. Because home was never only a question of whether the machines run. 4 conditions have surfaced across this film, each doing real work toward that word, and it is worth naming them together now, rather than leaving them scattered across 9 separate chapters. Redundancy that does not run out, not a backup that survives one failure, but a repair capacity that survives an indefinite sequence of them, which depends on local manufacturing maturing well past where it currently stands. A body that is compatible with its environment, not merely protected from the worst of it, which radiation shielding partially satisfies and partial gravity biology, on current evidence, does not yet confirm either way. A life that can recover from failure rather than only postpone it, which is precisely what a communication delay measured in tens of minutes and a resupply cycle measured in years makes structurally difficult, no matter how skilled the people managing it are. and belonging that can be sustained and inherited across more than one generation, which is the condition this film's evidence has the least to say about, because almost nothing has actually been tested. Weighed against those four conditions, the picture that emerges is neither the confident colonization narrative nor its mirror image catastrophe. The first two conditions, redundancy and bodily compatibility, are engineering and biological problems with real, if incomplete, evidence behind them. Progress on both is measurable, ongoing, and, on the terms this film has laid out, genuinely plausible over time. The second two, recoverability and generational belonging, are not primarily engineering problems at all, and that is the reclassification this entire film has been building toward. They are questions about what kind of commitment a person, a family, and eventually a society are willing to make to a place that cannot promise rescue and cannot yet promise safety for a child born inside it. No habitat design solves that question, because it was never an engineering question to begin with. It is worth stating plainly what this means for the people who would actually make that choice, because this film has spent 9 chapters on systems and only a few sentences, so far, on the humans deciding whether to trust them. Choosing to move permanently to Mars, on the evidence assembled here, would not be choosing a harder version of an ordinary immigration decision. A difficult but bounded set of trade-offs. Weighed and then settled. It would be choosing to accept 2 categories of risk that behave completely differently from each other. A set of engineering risks that are actively, measurably improving year over year, and a set of human risks. The body's true long-term relationship with partial gravity, the psychology of true permanence, the health of a first generation of Martian children, that no amount of additional funding or cleverness can simply engineer into being known ahead of time. The first category rewards patience and investment. The second rewards something closer to honesty about what remains genuinely unknown, and a willingness to proceed anyway, with eyes open, rather than after every question has been answered. Because on the current evidence, not every question can be. It is worth being explicit about which parts of that architecture belong to the category of solid, if incomplete, engineering, and which belong to the category of genuine unknowns, because collapsing the two together is the single easiest way to get this story wrong in either direction. Pressure, atmospheric composition, and the basic case for a sealed, engineered dwelling are not open questions. They are established physics, measured directly, understood decades ago. The coupling of 6 life support systems into one interdependent chain is not speculative. It follows the same well-studied failure mode logic engineers already apply to spacecraft and orbital stations. Radiation shielding, water and oxygen extraction, dust mitigation, and local manufacturing are not solved, but they are solvable in the ordinary engineering sense. Each rests on physics or chemistry already demonstrated in some working form, waiting on scale, funding, and time, rather than on a fundamental breakthrough nobody yet knows how to achieve. These are hard problems with visible paths toward answers. Partial gravity physiology and the psychological and generational costs of true permanence are a different category entirely. And this film has tried, deliberately, not to blur that difference for the sake of a tidier ending. These are not hard problems with visible paths toward answers. They are, honestly, unmeasured. Not because no one has tried, but because measuring them properly requires doing the very thing being asked about. Living at partial gravity, or living without a real exit for long enough that the data becomes real rather than inferred. No amount of additional engineering funding closes that gap by itself. Only time, and the willingness to accept that early answers will be provisional, closes it. Which is a very different kind of solution than an engineer can design in advance. So the honest answer to the title this film opened with is not a flat yes or a flat no, and pretending otherwise would repeat, in the other direction, the same overclaim this account has tried to avoid throughout. A Martian home is not currently a building on another planet, the way the word home ordinarily implies. It is closer to a permanently maintained artificial civilization in miniature, one that has already solved more of its own survival than skepticism usually credits it for, and one that has not yet solved, and may not be able to fully solve on any near-term timeline, the harder half of what the word home was always quietly asking for. Not just that a person can live there today, but that a life, and eventually a family, and eventually a generation that never chose any of this, could safely belong there. The room in the opening is still standing, air holding, water cycling, light rising on its artificial schedule. Whether it deserves to be called home is a harder question than the room's comfort lets on. And on the evidence gathered here, it remains, honestly, unresolved.